Welcome, as I said, to day 2 of DroneCamp. This is a lot of fun. I'm going to kick off today and talk about some of the core background principles behind all of the data processing that you're going to be doing in the next few days. And so today is Introduction to Drone Photogrammetry and Data Processing. We're going to go for about 50 minutes and then have a break and then start these fantastic concurrent workshops where you get your hands dirty. These sessions are recorded. Everything will be available to you afterwards, including the slides. Great. Okay, so today we're going to talk about drone photogrammetry and data processing. We're going to talk about principles and where all of this kind of has its antecedents. We're going to talk about workflow and the outputs that you're going to create. And then we're going to talk about some of the practical aspects around data processing. So the first thing, just generally, why we're all here is because drone data provides or produces these wealth of really terrific and useful products. From a collection of overlapping images, we can get all these. We can get orthomosaics. We can create indices from that data. We can get a point cloud, a terrain model, a surface model, and a textured mesh. And all of this can be done repeatable and through time. And it's really the background to all of this is very old. So everything we need from UAVs comes from concepts of photogrammetry. And photogrammetry, in a general sense, is the science of making measurements from photographs. And the first patent that described this process in detail was in 1893 from C.B. Adams, who described a method using 2 balloons and 2 cameras, and how just with 2 cameras, 2 photographs, you could make detailed measures of features on the ground by virtue of the fact that these images were overlapping. And so this concept of photogrammetry is what it's all been based on. And the 19th century saw the beginning of this, and the 20th century saw the real bloom of this. So this science of making measurements from photographs and recovering exact points and exact measures of features on the ground and their height all evolves from this concept of stereo photogrammetry, which is having overlapping photos in which you can see the same thing. And this is an old graphic. It's from one of the forefathers of remote sensing, Robert Caldwell, who taught at Cal for a while. You've got a camera on board an aircraft. You know all the parameters about the camera. You know everything about it, its focal length, any distortions you can model. And you're flying in a controlled way, and you can take overlapping photos so that you see the same thing in overlapping photos. And so you can ask of these features, how tall is it? Where is it? And all of the measures that you can get from this stereo photogrammetry process take advantage of the fact that this feature, in this case, this tree, can be seen in 2 different photos from 2 different vantage points. And if you know the height and you know some other basic information, you can calculate how tall that feature is. So this takes advantage of something called parallax. It's the displacement in a position of an object caused by the shift in its observation. And so in stereo photographs, we can track features seen in 2 images taken at different positions. And we can make use of this parallax and measure these things, measure their height and their location, just from a few measures on overlapping photographs. So this is the kind of background to all of this is traditional photogrammetry with overlapping aerial photographs. And with high quality cameras, like I said, we know everything about the camera. We know its focal length, its principal point, its distortion, its orientation. We know how high we're flying. We're capturing the photographs, looking directly down at the earth. We're highly accurate in terms of where we are. We've got really precise ground control. All of this traditional photogrammetry is very controlled. It's a very controlled situation. And it means that because we know so much, We only have to solve for a few parameters, and we only need to tie these photographs together with a few features or tie points. And this graphic here on the right is just an example of a couple of black and white aerial photography. This is what all of mapping for the 20th century, up until the last few decades really made use of. And you see that lake there. This tie point is that corner of the lake that you can see in both of these photographs. So traditional photogrammetry is a really controlled setting where we know a lot. Moving from that, we have our modern photogrammetry and what's called structure from motion that most of the software that you're going to be using later today deals with. And this is a less controlled environment. And the concept is, as long as we have massive amounts of overlapping images, that we can gather massive amounts of these features that we can see in multiple images, we don't need to know the camera model. We don't necessarily need to know how far away it is to a precise degree. If we have enough tie points, we can construct the 3D shape of the feature we're looking at. We can recover the details of our camera model. We can sort of back calculate all the things we need to do to make these precise measurements. We can do this with consumer grade digital cameras. We don't need these extremely expensive and cameras with known distortion models. We can do this with anything. And so this was really pioneered in a bunch of areas. It's been tremendously useful in museum science. I just throw this up. There's lots of fantastic examples out there of how we're using structure from motion to get at things like statues that might be in some danger, or we're trying to reconstruct these things or try to find out where there are micro topographic differences on an archaeological feature that might bear fruit. So this is all structure from motion. It's modern photogrammetry. And we've been making use of it in the remote sensing world with UAVs for a long time. So these are automated techniques. They evolve from machine learning. They require massive amounts of tie points, lots and lots of image overlap. The point is, you can reconstruct the camera model from the images alone, but they do require large computing power because, as you're going to see from the next few slides, they're really kind of a massive automated visioning exercise trying to find these precise features in overlapping images. So everything we're doing in UAV data analysis everything relies on image overlap and tie points. And so the acquisition of imagery with the right characteristics is critical. And we're going to talk about that now. We have to consider things like, what kind of camera, or are there particularities to my camera that I need to pay attention to? How big on the ground is my image extent, and what does that mean for my flight? What's my ground sample distance, and what should it be? How should I put in ground control? And at the end of the day, it's all about overlap and maximizing the overlap for your purpose. So let's start with the camera. So when we first began working in the UAV arena, there were a lot of cameras out there that had what are called rolling shutters. And we talked about this a little bit yesterday. There's two types of camera shutters. There's global and rolling. And rolling shutters are really rows of pixels that are exposed in sequence. And some of the early Phantom and Inspire and Sequoia, Sean mentioned this yesterday, had rolling shutters, and they take okay pictures, but with mapping, it's a problem with that rolling shutter because it can create blurring or smearing, and particularly in low altitude flights. So this picture on the right is an example of kind of that blurring or smearing that happens with a rolling shutter. Global shutters, on the other hand, are a proper CCD that exposes all of those pixels at the same time. So it's a real imaging sensor. And the more expensive and recently most UAV cameras of any quality have a global shutter. And so if you're doing mapping applications, you should try to use a camera with a global shutter. That said, there are in several software packages corrections you can apply if you know you have a rolling shutter and you don't have an alternative. The second issue with cameras is thinking about what is the footprint on the ground of that particular camera. So the more megapixels you have, the larger that extent is going to be. And so the bigger that extent on the ground is going to give you two advantages. One is that you have fewer passes over an area to collect the information you need. And the second, as we'll see echoed through all these slides, bigger footprint on the ground means more overlap and more tie points. So it also means it's a more expensive camera, but having a bigger footprint translates to less time in the air, less overall operating costs. And while it is possible to use something like a lower resolution video or a still from a lower resolution video for mapping, we don't really recommend it because it's not high enough quality, and in general it gives you a smaller extent with some of these challenges that we mentioned. The next thing we want to talk about is ground sample distance. Again, Sean mentioned this yesterday. Ground sample distance is the distance between two consecutive pixels measured on the ground. It's essentially your resolution. Larger ground sample distance means lower spatial resolution and less details. But that's not necessarily a bad thing. We're going to get to that in the next couple of slides. But the general principle is your ground sample distance is going to depend on your camera, the focal length and the pixel size of that camera, and your flying height. And there's some general formula about calculating ground sample distance. This is a very simple one. Your ground sample distance is based on your flying height above the ground, the camera dimension in microns, and the camera focal length. And there's tons of useful calculators out there if you want to kind of run through some of what your favorite drone cameras have as a typical ground sample distance at a typical flying height. For example, a Phantom 4 would have a ground sample distance of about 2.7 centimeters if it was flying at 100 meters above ground. The calculators, I believe, we put some of those in the forum, I think, but they're out there. So plan your ground sample distance for purpose. Just because you can get, a 1 centimeter ground sample distance doesn't necessarily mean you want to get a 1 centimeter ground sample distance. The smaller the ground sample distance, more details, but it can introduce more problems. It can introduce problems with the photogrammetry, which I'm going to show you in a bit, because micro changes and features between imaging can cause you problems in getting these tie points. It can give you a challenge in classification because you have so much micro detail. Irena on Thursday is going to talk about ways to, use object-based image analysis to get at this high spatial resolution. And then, finally, smaller ground sample distance means just much more data for you to process. And so an example is if you fly with a GSD of 1 centimeter instead of a ground sample distance of 3 centimeters, you're actually getting a data set that's about 10 times more in size, which can, bog you down in processing. So from yesterday, Sean gave us the pointer, aim for about 5 to 10 centimeter ground sample distance. Rule of thumb, but again, plan it for your purpose. It's all about trade-offs. Smaller that ground sample distance, higher accuracy on the ground, lower flying height, longer flying time, massive data sets, longer processing times, larger ground sample distance, lower accuracy, higher altitude, shorter flights, smaller data sets, moderate processing times. So as a rule of thumb, you'll be able to get measures of absolute location at an accuracy of about 1 to 3 times your ground sample distance. So that means if you fly at a 1 centimeter, you're going to get about a 3 centimeter absolute accuracy. And if you fly at a ground sample distance of about 10 centimeters, you're gonna get up about a 30 centimeter absolute accuracy. But remember, it's all about trade-offs. You wanna plan this for purpose. And I just mentioned absolute accuracy. So what is that? Absolute accuracy is when you can actually make real world measurements off of your product. They're tied to the real world. It's a meter on the ground equals a real world meter in your imagery. Relative accuracy just means the size of this tree in general, its diameter is correct. The size of this building is correct, but we can't really tie that to real world measures on the ground. And to do that, you have to have ground control. So accurate ground control will help you get better absolute accuracy. And we mentioned this yesterday. This is done through the placement and measurement of ground control points. There's a few examples there on the right. These are easily identified targets on the ground that have high accuracy GPS coordinates attached. They can be temporary, they can be permanent, but in general, you want to use large, clear targets with high contrast. Sean showed you some of those yesterday. You want to measure the center of it with high precision GPS. You want to evenly spread these through your map, and you want to make sure that they're unobstructed and clearly visible in the imagery. And you're going to place these out in your site, measure them, and then utilize that information in your processing step. Finally, mission planning, overlap. Everything we do is based on overlap. We're going to talk about side lap and front lap. We did a little bit yesterday. And so overlap just means that you're going to see the same features in multiple images, and that means you can generate these matching points. So in general, it's about planning that overlap. And if you have a small overlap, you're only going to get a few tie points. If you have big overlap, you're going to have more opportunity to get this massive amount of tie points that you need. Pix4D recommends about 1,000 matched points per pair, and they recommend that all things even, this usually requires about a 75% overlap. So that's a lot of overlap, but that's because that's all we need. That's what we need. Sean showed you this yesterday. This is looking at a grid pattern. And this here is showing that the front overlap is 75%, the side overlap is 60%. And there was a question yesterday as to why these could be different. And they can be the same, but in general, if you need to maximize battery life and cover as much as you can in a flight, you can get away with slightly less on the side lap than on the front lap. But you can also fly so that you have the same amount of overlap in each the front and the side. And again, everything we do is based on this overlap and massive amounts of tie points. So a couple of other things to think about with mission planning. If you're flying an area that has changes in topography, as you might, that's going to impact your overlap. So if you're flying at the same height and you're flying over high topography and low topography, that overlap is going to change because the flying height is going to change. And areas where you're flying over higher topography are going to have less overlap than areas that you are flying over that are lower. You're going to have more overlap. So you can either fly at one height and just make sure you've got your minimum standards everywhere. You can fly multiple missions to ensure that you have the right overlap over certain areas. Or, as Sean mentioned yesterday, some drones and apps make it available easier for you to follow the terrain. And that, in a lot of ways, is the best plan, but it is one that requires a little bit more expense in terms of your hardware. So the good thing is all of this can be done in mission planning, and we've had our mission planning sessions yesterday, and at the end of the day, Sean, I captured this from your slides, Sean, yesterday. So when in doubt, increase the overlap and fly higher. And so these are all things that you're gonna, kind of learn as you get more experience under your belt doing this flight. All right. We're about halfway through. I thought it might be time to take a couple of questions if there are any.
Yeah, thanks, Maggie. This is great.
Yeah.
So one question that came up is how do we tell if our camera has a rolling versus a global shutter?
Good question. Yeah, all of that information is going to be in your camera specs. That's right.
Yes, yeah. Look at the specs of your equipment. That's usually where it's going to be found. Sean?
One little side note I might throw in too is that a rolling shutter isn't always bad.
Yeah.
Most RGB cameras use a rolling shutter and they produce really good quality imagery. It's just in some cases it's an issue. And again, yeah, just look at the specs.
And you can deal with that in your stitching software, right? There are corrections for that available.
Correct.
Yeah, but at least I would say with Pix4D, you have to manually tell it that you want to apply the rolling shutter correction, because if you're flying in safe mode where the drone stops at every camera point, you don't really need it. And it does cause another level of another effect. There's two questions, which we might punt until this afternoon. At what precision GPS can we forego GCPs in reference to those with RTK systems? And then how do you define high precision GPS?
Well, the second one is a little bit easier, I think, than the first one. There's a pretty big jump in terms of GPS between recreational and survey grade. So everything you have from your Garmin's, Magellans, Bad Elf's, all of these are considered recreational grade. And even though some of them are fantastic and they're WAS enabled and all the rest, they really can't guarantee you, you know, on a good day, you're 3 meters, 1 meter maybe, but survey grade, which are your Trimbles, they are due to antenna and a few other improvements, which means they're more expensive. They can get you down to sub-meter, and you need to be there because we're talking about pixel sizes that you saw that are, you know, in the order of centimeters. So if you're throwing in a GCP that it might be 3 meters off, it might be 5 meters off. It's really not doing you any good. So survey grade or better, and better than survey grade is RTK. But as you step up from these recreational survey RTK, you pay more.
And then maybe one more question. I do want to also say to everyone, I put the link to, so the slides that Maggie is showing are now on the website. Simply, people have been saying they look blurry. They're looking okay to us, so we're not quite sure what's causing that blurriness. But if you go to the website, click on refresh the browser, you can follow the slides as Maggie's talking through them. Somebody is asking, does overlap need to change if you're flying with the camera oblique versus nadir?
Yeah, so that's a great question. So if you were flying oblique, like you could fly a flight pattern around something, say if you wanted to, you know, really get that structure for motion for a tall feature, the overlap would be based on that particular purpose. I can't think of a reason why you would be flying oblique for a straight up mapping exercise, but I might not be thinking about this right. Sean, any comments?
Yes, so yes, you might need to fly with a different overlap, but you also might need to change your elevation of your flight. So think of the overlap in terms of the direction of the view angle. And so if you needed to get a 3D representation of like a building, for instance, you might fly at one elevation lower and then go up to a higher elevation that essentially would create a similar like 80% overlap on the angle of the photos.
All right, there's a couple other questions, but let's keep going. And for those of you who are asking about RTK, there is the high precision mapping session later today.
Terrific. All right, so now we're going to launch into the workflow part. And we here in DroneCamp, we're showcasing a lot of different software, and there are even more software out there that do this UAV photogrammetry. But there are some generic steps to all of this, and that's what I'm going to present here. And then you're going to plug in where you need to with your specific software. So you start with your image collection. This is just your raw images flown. They're overlapping and there are many of them. And you also have camera information associated with each of those images. Those data go in to the first step of this workflow, and that's creating these massive numbers of points that can be first seen in the raw images and then matched to their overlapping pair. And so all of those images are pulled together, and these key points are found, and then these tie points that tie them together are found. And using those tie points, the software is going to do an initial camera model calibration. They're going to say, we've got the information that you gave us about your camera, but we're going to calibrate this because we've got this massive amount of tie points. So we can reverse engineer where your camera is. And from that, we're going to stitch all these images together in kind of this block. And then we're going to use all those overlapping tie points to triangulate them and create real world geolocation, sometimes using GCPs if you've got them, to tie this whole block down into a solid chunk. The next step, go to the top here. We're going to take all of those 3D points that we've measured and densify them, find more, create more points that will yield us the surface of trees or buildings or whatever else you've got. That point cloud is then classified to above ground and the ground. And from those two products, we create a digital terrain model and a digital surface model. That digital surface model is going to be used a little bit later. But another product that comes out of the point cloud is the textured mesh. That's a surface that shows the structural features of everything that you've got and then maps the color from the original point cloud on as a texture to give you this virtual reality of your landscape. The next path, we take all of those photos that have now been stitched together and we're going to orthorectify them using the digital surface model. We do some color balancing and scene matching to make it pretty, and we get an orthomosaic. And all of these software, well, not all, but most also produce some detailed information about how this whole process works. So this is the workflow. I'm going to walk you through it in a generic way, and you'll be doing it in a detailed way later. So the first step are finding these key points. These are just finding massive amounts of these things, these little features in images that can be recognizable. Again, this is the hallmark of modern photogrammetry. It's the big difference between traditional photogrammetry. We have thousands of these points per image. They're identifiable features. They're based on your ground sample distance, your visual content, your texture, your contrast, environmental conditions, whether there's a breeze is going to make a difference. These are then turned into tie points. These are matched by overlapping image pairs. So we want to be able to see the same thing in two images. And I've got some snapshots here. These are from Pix4D of example tie points. The top panel are just that center point of that individual tree. That's a great tie point. The middle panel are sort of this real detailed textural information from the ground, but it's the same in all of these images. And the bottom one is an example of where it doesn't quite go very well because this is a very high resolution data set and we actually had a gust of wind and you can't actually see, you know, which particular branch you're trying to make your tie point from. So from tens of thousands of key points, you want to try to get some kind of number of thousands of tie points per pairs of images. And again, these depend on your ground sample distance, your visual content, and the environmental conditions. From these tie points, we then create a initial camera. We take that initial camera model that we were delivered and we calibrate it. We're able to say, you said the camera was about here, but the GPS on the drone isn't perfect. So we're going to use this reverse engineering process and really tell you where that camera is in space. So this is an example from the Pix4D process, but it's similar in most of the others. You have some kind of original camera location where we calculated that based on a preliminary model, and then a modeled camera location based on this processing. And again, just to point out, all of these software will provide you, so this dot down here on the ground, this is a tie point, and it is seen, all of these rays are all of the vantage points, all of the different images in which that individual point can be seen. And the more of these mean the more we can solve for these multiple parameters and pull this complete set into reality. And we do this through, we've got this initial set of all of these overlapping images. We found this calibrated camera model, and then we triangulate all the different points with all the images and pull this set of photographs, these overlapping photographs, into a block, into a cohesive block where all the overlaps make sense and all of the height makes sense. And then all of these software processes fit some kind of adjustment process that says, what's the best statistical fit for this entire big block of images, and produce some kind of accuracy measure, typically a root mean squared error that is calculated for all of those tie points. Because remember, if you've seen that point in 10, 15 images, you can say, well, in this image, it's this XY, and this image, it's this XY, and they're slightly different, so I can calculate a root mean squared error from it. Next step, we take all those points then, and they all now have an X, Y, and Z because we've calculated that through this triangulation process. Now we can densify them. We can say, I've got this many points, I want 10 times that many points. And you can decide how many you want in your resulting point cloud. Denser point clouds result in more 3D points and a denser textured mesh. But it also increases your file size and can slow down your processing. Again, it's based on what you need. And so this little shot here is a single almond tree from Lynn Cove Research and Extension Center. It's using aerial photographs or digital aerial photogrammetry. It's about 100 to 150 points per square meter. It's a really decent representation of that individual tree. But again, as you densify more and more and you get more points, your file sizes are going to get larger. This is the product that can come out of it. This is again from Lynn Cove. This is an almond orchard, and this point cloud is derived from aerial photography. Some of you asked early on, what's the difference, or how do these things compare between aerial photography point clouds and LiDAR point clouds? So this is a comparison here. On the left is from aerial photography. It's about 100 to 150 points per square meter. On the right, this is from terrestrial LiDAR. So you're walking with a backpack and a LiDAR in the same orchard. That's the same tree. It's 2 orders of magnitude more. So it's a lot more points in LiDAR, but you can still get away with, we could do a lot with the aerial photography point cloud. So that point cloud is then split into above ground and ground, and those 2 point clouds are used. They're interpolated to create a digital terrain model, which is just the ground surface. It's your bare earth model, and your digital surface model, your DSM, is everything else. It's the reflective surfaces. It's in a forest, it's all the green matter that you've got, but in a city, it's all of the buildings. It's everything on top of your surface. This is what these look like. They come out in a range of different file formats, DSM, DTM, extremely useful. Again, the digital terrain model, it's not as good as LiDAR because you're interpolating between areas where you couldn't actually see the ground, whereas LiDAR, you're actually measuring directly to the ground, but it's a decent substitute in a lot of areas, especially if you don't have a lot of crown closure and canopy cover. The next product that comes out of this is the textured mesh. Again, you take that densified point cloud, you create a triangular facets that cover it. It gives you the structure, and then you remap on the color and the texture from the point cloud to give you a very realistic virtual appearance of all of the surfaces in your area. The final product that we're going to talk about is the Orthomosaic. This is a lovely, lovely thing that we get out of UAVs. This is why a lot of us are in this business. We want to get this fantastic image. And so this is the photo. Orthophoto is created by taking all those stitched images that I talked about and then using the digital surface model to remove all of those imperfections caused by perspective and relief, and really making this a product that you can that you can use for on the ground measurements. Distances are preserved. It's a real map product rather than just a stitched together image. That Orthomosaic then a lot of us use to then do spectral indices or analyze vegetation change or whatever you want. This is an example from our Sierra Foothills Research and Extension Center. On the left is an Orthomosaic of RGB imagery showing some range exclusion experiment zones. So the sparser vegetation is where the cows have been grazing more, and the greener areas where they haven't, and you can enhance those with a series of vegetation indices. And Irena Dranova on Thursday is going to talk more about vegetation. Finally, the final thing that all of these software produce, or most produce, is some kind of quality report. And this, in general, gives you a lot of background information about how well you've done in this process. It gives you basic information about how many images went in, what was your total number of tie points, what was your root mean squared area of the error of the whole thing, what's your ground resolution. It gives you specifics about your tie points in general, how many were they, how many were seen just in 2 cameras, in 3 cameras, in 4 cameras, etc. It'll give you something about how well they fit together in terms of RMSE for individual points. Some software can say, you know, these tie points didn't meet a certain threshold. You can eliminate them or you can use them. The quality report will tell you something about the camera model that's been reconstructed. They'll tell you something about how successful the ground control was, and they'll tell you something about how well you managed to create image overlap. I'm going to give you a couple of examples from Pix4D and from ArcGIS Pro. So in the quality report from Pix4D gives you something like this on its first page. It's super useful. In general, the Pix4D quality report is the most verbose. So in this particular case, and this is the study area that Sean was talking about yesterday, and you're going to see more in the breakout groups today. The images, there was about 60,000 key points per image, so that's great. All 88 images were calibrated. There was about a 4-point difference between that initial camera location and the optimized information. We got about 10,000 matches per image, which is great. And it says, did you do georeferencing? Yes, we did. There were 7 GCPs. The root mean squared error was about ½ meter. So those give you a lot of really good information about how well you did on this process. And another set of information that come in these quality reports. This is not from Pix4D now. This is from Esri, but Pix4D does something similar. They tell you something about how close was the model in terms of the original camera position and then that modeled camera position. That's the first shot on the left. They also tell you something about how close were all of those, how well meshed were the tie points. So in this particular middle section, all of these links mean that those two images had this many tie points together, and the darker the line indicates more, so a richer kind of mesh. And then that picture on the right is just, this is your overlap. How many images did you have overlapping? And obviously you're going to have less overlap typically at the edges, but these are good diagnostics where you can see maybe I should have flown at a different altitude if there was an area of my study area that was a lot lower or a lot higher, or, you know, these are all things that you can use to evaluate. And so when you've done your mission, you want to think about some checks. And so you're going to think about how well did I do finding tie points? You're going to look at the quality report. How well did I overlap? Look at the quality report. You can do some relative spatial accuracy. If you know something on the ground that you can measure in the image and on the ground. You can look at absolute accuracy by looking at that georeferenced RMSE from the ground control. And in general, you want to do, does it pass the sniff test? Does it look right? Is straight straight? Are roads continuous? Are the things look good? All right, we're wrapping up here. So practical aspects. You need a big computer. So this is the Pix4D recommendations. Pretty, you know, decent size CPU, lots of RAM, good GPU, and they have some recommendations. If you meet these, Pix4D probably has the most conservative. So if you meet these, you're going to be all right. But all of the software is going to provide some kind of recommendations for minimum standards, but try to meet and exceed those standards. And in general, while we are pushing stuff up into the cloud, most of the stuff you're going to be doing is going to be performed on the desktop. There are enterprise solutions with some processing software like Pix4D. So we're moving into the cloud, but right now we do a lot of stuff locally. And this is important for the data management stuff that we're going to be talking about in the next few days. So I'm going to wrap up here and just point out that this is just the basic, and then the next couple days we've got a lot of deep dives into individual software that are doing this, and it's going to be a lot of fun. So I'm going to stop there with a couple minutes for quick questions.